Alright, what's up everybody? This video we are approximating integrals. Alright, so when would we go about approximating integrals? Well, if you have an integral that you want to evaluate and you can't integrate the function. So for example, let me come down here where I have a little bit of room. So for instance, an integral like this, if we have say 0 to 1 of say e to the x squared dx, well, we can't integrate that. Or if we had something like this, negative 1 to 1 square root of 1 plus x squared dx. All right, so, or, well, let's see, not x squared, let's see, x cubed. That we can't integrate that. So we need other means of evaluating these integrals. And another way that we would need to approximate is say that we collected data and we need to do something with that, and we can't come up with a function for that data. All right, so those would be reasons where we would need something like this. So, you know, earlier in the course, you have approximated the area under a curve using left endpoints. Okay, where you find the area of each one of these rectangles and then you add them up. And then, and notice you got your left endpoints right here. And then another one would be right endpoints, same thing. You add up the areas of all the rectangles. All right. And then you have midpoints, and I did not draw the rectangles here, but here you have your midpoints. And we could approximate the area like this also. All right. So let's go ahead and look at some stuff. So we have the midpoint rule. So the midpoint rule from a to b, we're integrating a function from a to b of f of x dx is approximately equal to delta x times f of x bar 1 all the way to f of x bar n. All right. Now, what is x bar 1, x bar 2, and so on? Well, that's the midpoint. You can see here in this figure, that's the midpoint of each rectangle. And so what we're doing is we're evaluating this function here. You see this function here. We're evaluating this function at each one of these values, and we're summing that up. And we're multiplying it times delta x. So basically what that is let's just look at it a little bit closer. So this delta x is this value here. That's the width of your rectangle. And then what do we have to do to get the area of a rectangle? Well, we got to do the width times the height of the rectangle. Well, how do we find that height of the rectangle? Well, the height of this rectangle is this y value, right? That's your y value. Well, how do we get the y value? Well, we plug the x value into the function, and see, that's what we're doing here. So we've got the width times the height plus the width times the height. See, I can distribute that delta x to each term. But what happened is, see, we're doing width times height, width times height, width times height, but we're factoring out the width of the rectangle, this delta x here. And that's why it's outside the parentheses here. So these are just the heights of each rectangle. And then how do we find delta x? Well, that's b minus a divided by n. All right, where n, that's the number of rectangles we want. All right, and x bar sub I is equal to 1/2 x of I minus 1 plus x of I. which equals the midpoint of that interval there. And I mean, we know that. If you have, like, so in other words, if you have two values here and here, how do you find that midpoint? Well, you add this and divide by 2. That's all you're doing to find that midpoint. And then we have the trapezoidal rule. It says the integral f of x dx from a to b is approximately delta x over 2 times f of x naught plus 2f of x1 plus 2 times f of x2 plus 2 times f of x sub n minus 1 plus f of x sub n. So notice this first term and this last term, what's happening there? Well, they're not getting multiplied by 2, but everything in here is. And of course, delta x is the same as above, b minus a over n, and x sub I is equal to a plus I times delta x. And I'll talk about that more as we're working through the examples. So let's go ahead and get started. So it says use A, the trapezoidal rule, and B, the midpoint rule with n equal 5 to approximate the integral 1 over x dx from 1 to 2. Now, I know we can find the exact value of this. I know that. Okay, we know how to integrate 1 over x. That's just natural log of x. But we're doing this one to where we can integrate it so we can compare what the actual value is to the approximated value. That's why we're doing this one. All right, so let's go ahead and start with the trapezoidal rule. So this will be part A. All right, so what we need is we need delta x. Okay, we need delta x. So delta x, which is b minus a over n, that's going to be, now in this problem, what do we have? We have a is equal to 1, b is equal to 2. So that's 2 minus 1 over n. Well, n, they tell us, is 5, so that's over 5. And so this is going to be 0.2. That's delta x. All right. So now remember what it says. X sub I is a plus I times delta x. All right. So we have the integral from 1 to 2 of 1 over x dx is equal to, and that's going to be T5, all right, is equal to, and I guess I should put an approximate here because that's going to be approximate. So that's delta x, which is 0.2 over 2, see our formula, times f of what? Well, x naught, that's 1. We're going from 1 to 2. So in this problem, a is 1, b is 2. So x naught, that's going to be 1. X sub n, that's going to be 2. So that's going to be 1 plus f of what? Well, how do we get to the next one? Well, we just add 0.2 to this. So that's 1.2 plus f of, and then we add 0.2 again. So that's going to be 1.4 plus, and then we add 0.2 again, f of 1.6, and then we add 0.2 again, f of 1.8, and then what? And then f of 2. All right, and so we plugged everything in. You see that? See the I delta x? Let me just write one of them out. So a is 1 plus, okay, and let's just show how we get the first one, the x naught. So that's going to be 0 times delta x 0.2, which is 1. See, that's where that 1 comes from. And then we have 1 plus, and then we need x sub 1. And so that's going to be 1 times 0.2, which is 1.2. And then we have 1 plus, and now for this one, that's going to be I is 2 times 0.2, which is 1.4, and so on. And yes, I do realize what I did. Each one of these, what did I forget to do? I think I was just worried about getting everything on one line that I just forgot all about it. We got to do plus 2 times, right? All right, so don't forget that. See, each one of the ones in between here, they got to have 2 times the function. And I was worried about getting everything on the screen, and just it slipped my mind. All right, so now let's go ahead and plug everything in. So we've got 0.2 over 2 times, now f of 1, so I'm going to take the 1 and plug it in here for x. So that's going to be 1 over 1 plus 2 times 1 over 1.2 plus 2 times 1 over 1.4 plus 2 times 1 over 1.6 plus 2 times 1 over 1.8 plus 2 times 1/2. All right, and so when we punch all that into our calculator, we end up with 0.695635, and there's your answer. Oh, covered up the decimal point. And so there's your approximate answer. All right, so that's the trapezoidal rule. Now let's use the midpoint rule. So for part B, all right, so once again, we have delta x, that's going to be 0.2. We got that from up here. Delta x is going to be the same. All right, so now let's, for the midpoint rule, let's maybe, well, I guess we could draw a picture of it, but the main thing that we're looking at here is if you look at a number line here, let's call this 1, okay? And we know that the next value here is going to be 1.2, 1.4, 1.6, 1.8, and then 2. All right, and we have the rectangles going up like this. And you know, on this one, it's not really that difficult to draw the figure. It's going to look something like this. You see that? Let's erase this right here. The graph's going to look something like that. But what I'm getting at is sometimes these things, they may be a little more difficult to graph. So, I mean, it's good to draw the graph, but you can get by with it without drawing the graph. But what you want to make sure you have is this part down here. Because see, here we can come up and we can see, and I'm going to do that in a different color. See if I can erase that. Let's do it in red so we can see it. So you see the midpoints are right here. These are the values that we're after. Because remember, for the midpoint rule, we have to evaluate the functions at the midpoints of each rectangle. And that's really what we're interested in finding, are these midpoints. So remember, here you can just do 1 plus 1.2 and then divide that by 2. So it's this plus this, divide that by 2, and that'll give you this value here, which that's going to be 1.1. And you can do the same thing, 1.2 plus 1.4, that's going to give you 1.3. But yeah, on this one, it's easy to see what the midpoint actually is. I mean, the midpoint between 1.2 and 1.4 is 1.3. But if you can't see right off, then that's how you could find it. And so this one would be 1.5, 1.7, and 1.9. And so now we just apply the midpoint rule. So we've got the integral from 1 to 2 of 1 over x dx is approximately, and that's going to be m5. That's just the midpoint rule with n equal 5. So what's the formula there? Well, it's delta x, which is 0.2, times, and then we're going to evaluate the function at each of those values and sum them up. And so that's going to be f of 1.1 plus f of 1.3 plus f of 1.5 plus f of 1.7 plus f of 1.9. And so that is going to give us 0.2 times, and then we take each one of these values here and we plug them into the function 1 over x. So that's 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. And when we punch that into our calculator, we end up with 0.691908. And there's your answer. So you can see they're a little bit different here. Okay, the values are a little different. So let's look at it. Let's look and see what kind of error we get. All right. So to find the error, we actually need the exact value. So the exact value is 1 over x dx from 1 to 2. And so that's going to be natural log x from 1 to 2, which is the natural log of 2 minus the natural log of 1, which is equal to the natural log of 2. And then if you punch that into your calculator, you end up with 0.693147. All right, that's the actual value, and yes, it's rounded. Okay, so let's look at the error. The error in the trapezoidal rule is gonna actually, in this problem, it's gonna be the integral of 1 from 1 to 2 of 1 over x dx. So it's gonna be our actual value that we get minus what we approximated. Okay, and so that's gonna be 0.693147. See, we got that right here, minus, and then the answer we got for the trapezoidal rule, which was 0.695635, which is 0.69, let's see, 565635. And when we subtract those, we get negative 0.00248. So that's the error that we get with the trapezoidal rule, and you can see it's not that big. Okay. Now let's look at our error from the midpoint rule. So that's going to be from 1 to 2, 1 over x dx minus what we calculated with the midpoint rule. So that's going to be the 0.693147 minus 0.691908, and that actually gives us 0.001239. And so you can see we actually got a better estimate with the midpoint rule. Okay, we got a better estimate with the midpoint rule. But one method is not more difficult than the other. Okay, I don't really think. The only little bit of extra work that you have to do with the midpoint rule is calculating. Where did I do that? Right here, calculating the actual midpoints. That's the only little bit of extra work, but the midpoint did give us a more accurate result. All right. All right. So let's look at error bounds. So it says, suppose that f double prime of x is less than or equal to k for x between a and b if the error in the trapezoidal rule and the error in the midpoint rule are the errors in the that's what that means. E sub t, E sub m, errors in the trapezoidal and midpoint rules. Then the error in the trapezoidal rule, absolute value, is less than or equal to k times b minus a cubed over 12n squared. And for the midpoint rule, it's less than or equal to k times b minus a cubed over 24 times n squared. All right, so let's work some examples with that. And one thing I want to say, these error bounds, I have some more examples of these types of problems on my YouTube channel. If you want to check those out, it's with different functions. You might want to look at those because it's some different problems. I think I do some trig functions in them also. So I'll leave the links to those in the description if you want to check those out too. All right, it says give an upper bound for the error in the previous example to the estimate for the trapezoidal rule. All right, so we want to find the upper bound for the error. All right, so how do we go about doing this? All right, so we're doing this for the trapezoidal rule. So what do we need in order to do this? Well, we need what? We need to know what the second derivative is. All right, so I have f of x is equal to 1 over x. I have f prime of x is equal to negative 1 over x squared. Okay, I'm not going to go through finding these derivatives, but remember, 1 over x can be written as x to the negative 1. You just keep using the power rule. And then f double prime of x, that is going to be 2 over x cubed. So there's f double prime. All right. Now, we know that a is equal to 1, and we know b is equal to 2. So let's just write down what we have here. We know we've got the e sub t is less than or equal to k times b minus a cubed over 12n squared. All right, so we've got to know what all of these variables are. We need to know k, b, a, and n. Well, we know b is 2, a is 1, and we also know that n is equal to 5. Because remember, in the previous example, they told us n equal 5. So what we have to find is k. Now, finding k, that can be the more difficult part of the problem. Okay, that's what we've got to find. All right, so we know that x is between 1 and 2, right? We're integrating from 1 to 2. And what that also tells us is that 1 over x is less than or equal to 1, right? This function here is less than or equal to 1. And how do we know that? Well, if you take this value 1 and plug it in for x, you see that? That's going to be 1, and if we take the 2 and plug it in for x, that's 1/2, which is less than 1. Notice we're going from 1 to 2, so 1, when we plug the 1 in, You see that when we plug the 1 in, we're going to get 1. But if we move up, if we plug in like 1.1, 1.2, 1.5, 1.7, that denominator is larger than that numerator, so we know it's never going to be larger than 1. Okay? So how do we know what K is? All right, so we have the absolute value of f double prime x. Okay, so what I'm doing here is this. You see this? I'm gonna figure out what K is. So f double prime of x is less than or equal to 2 over x cubed, right? We got this right here. Now, I'm sorry, absolute value, which is less than or equal to what? 2 over 1 cubed. You see that? Now, why did I use 1? How come I didn't use 2? Or how come I didn't use 1.5? Well, because plugging the 1 in, that's going to give me the largest value of this function here. Okay? You see that? Let's suppose that I just, for instance, let's suppose I put 2 here. I had 2 cubed. I plugged that in for x. Well, is that a true statement? No, that's not a true statement, because that would be 2 over 8, which is 1/4. You see that? You've got to understand I'm looking at the values between 1 and 2. And if I plug the 2 in, well, that's going to give me a value of 1/4. But what happens when I plug in 1? That's going to give me a value of 2. So that's not a true statement. Plugging in the 1, that's the largest value I can possibly get over this interval here. You see that? That's what you're looking for. And so that's why this is 1 cubed. And so that is equal to 2. So I've got f double prime of x is less than or equal to 2. So I'm going to take my K value to be 2. And now I can plug everything in to this right here. So I get E sub t is less than or equal to K, which is 2, over B minus A cubed over 12 times 5 squared, which is equal to, what is that? If you plug that in, that's going to be 0.006667. All right, so this is the upper bound on the error. Now, the other thing that I wanna make note of is when we did this right here. Okay, when we look for K. Now keep in mind, you have to make sure that whatever you choose, that's going to be the largest value in this interval here, 1 to 2. Now, you can use values larger, like I said 2. You could do 3, 4, 5. But the smaller you can get your K value, the better estimate you're going to get. Okay? So, yeah, you want the largest. Okay? That's what we want to do for K to get the largest, but we want it the smallest largest, if that makes sense. Okay? All right, so let's look at another example. It says, how large should we take n in order to guarantee that the trapezoidal and midpoint rule approximations for this integral are accurate to within 0.0001. All right, so they're asking for something a little bit different here. All right, they're saying, okay, I want my error to be no worse than this. Okay, I don't want my error to be worse than this. So what does n need to be? That's what we're looking for in this problem. And it's the trapezoidal and midpoint rule approximations. So we're going to look at both of them. All right, so first thing I want to do here is I want to write down the trapezoidal rule and the midpoint. So we got, whoop. All right, so let's write this down so we can see it. So I've got k times b minus a cubed over 12n squared, and e sub m is equal to k times b minus a cubed over 24n squared. All right, so we're looking for n. So the thing that we would have to do here, you know, if we just started out on this problem, is we would have to figure out what k is. Well, k is equal to 2, because look, we did that up here. Okay, we already found k up here in this problem. So we're not going to go through that again. So we know we're going to choose k to be 2. Okay, this is what you would have to do to start the problem out. All right, so now let's do the trapezoidal rule first. So we have 2 times, now b minus a, that's 2 minus 1, right? 2 minus 1 is 1. So that's going to be 1 cubed over 12n squared. And what do we want? We want this error to be less than 0.0001 that we get from right here. All right. So I plug everything in. It's just this time we're trying to figure out what we need n to be to get this value right here. See, in this previous problem up here, see, it's like they're saying, okay, this is the error. What does n need to be? Okay. See, they're giving us this in this problem we're working now, and we've got to figure out what n is. In this problem, we knew what n was, and we calculated the error, the upper bound. All right, and now we just solve for n. So how do we do that? Well, I guess we can move the n squared up here and the 0.001 down here. So that's going to be 2 over 12 times 0.0001 less than n squared. See that? And so I have n is greater than, I'm going to just write the n over here, greater than the square root of 2 over 12 times 0.0001. All right. And so n is greater than, and that ends up being 40.8. And so we get n is equal to 41. That's what n would need to be in order for us to be accurate to 0.0001. All right, so now let's do the same thing, but let's do this with the midpoint rule. So it's the same thing. It's 2 times, and then that's going to be 1 cubed. 2 minus 1 is 1, so 1 cubed over 24 times n squared. I don't need the parentheses, n squared, and we want that to be less than 0.0001. And so that's going to be 2 over 24. And I'm going to solve for n. So I'm going to move the n squared up here and the 0.0001 down here. That's n squared. And so I get n is greater than the square root of 2 over 24 times 0.0001. And so I get n is greater than, that ends up being, when we plug that in, let's see. All right, I get 28.9. So I would need to take, so n would equal 29. And that's, I'm sorry, I dropped my calculator. All right, so that's what n would need to be for the midpoint rule. All right, another example. All right, use the midpoint rule with n equal 10 to approximate the integral e to the x squared dx from 0 to 1 and give an upper bound for the error involved in this approximation. All right, so e to the x squared, we can't integrate that. Okay, the first problem that we worked with, 1 over x, we could integrate that. We didn't need to use the techniques of this section to solve that problem. But this one we do. All right, so let's go ahead and see what we get. All right, so for part A, all right, so we've got A is equal to 0, B is equal to 1, and N is equal to 10. So first, let's find delta X. So we have delta X is equal to B minus, well, let's just write the formula down. B minus A over N. So that's B minus A over N by N, which is 10. So that is 0.1. So that's delta X. Now remember what I told you with the midpoint rule. We need to know the midpoints of each rectangle. Okay? So look at this. Let's look at the number line. So we're going from 0 and we're going all the way out to 1. All right, I'm going to have 10 rectangles. So we know that's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and yes, you could draw it. You could draw the graph. It's going to do like this, and it's just going to keep going up like that if you wanted to sketch the graph. But remember, what we're interested in here is the midpoints. That's what we need. We need the midpoints here. All right. So this midpoint is 1.05. I'm sorry, not 1.05. It is just whoop. I wrote it in the wrong one, didn't I? It's 0.05. That's the midpoint there. And then we would need the midpoint here, which is 0.15. And then the next midpoint, well, what would that be? That would be 0.23, 0.2 plus 0.3, and then divide that by 2. That would be 0.25. Oh, look what's happening here. Notice I found the first midpoint, 0.05. The next one's 0.15, and then 0.25. I wonder what the next one's going to be. 0.35. Notice you find that first midpoint, and then you add delta X to it to get the rest of them. See that? 0.45, 0.55, 0.65, 0.75, 0.85, and 0.95. And there you go. So now, just plug everything into the midpoint rule. All right. So we've got the integral 0 to 1 e to the x squared dx is approximately, and that's m10, right? Midpoint, we're using the midpoint rule where n is 10. So that's delta x, which is 0.1, times, and then we've got what? We've got f of 0.05 plus f of 0.15 plus f of 0.25 plus, and I'm gonna not write everything, plus f of 0.85 plus f of 0.95. Okay, so basically what we're doing, we're taking each one of these midpoints and we're plugging them in. Right here it is. We're plugging them in for x right here. That's what we're doing. And so this is going to be 0.1 times e to the 0.05 squared plus e to the 0.15 squared plus e to the 0.25 squared plus e to the 0.35 squared plus e to the 0.45 squared plus e to the 0.55 squared plus e to the 0.65 squared plus e to the 0.75 squared plus e to the 0.85 squared plus e to the 0.95 squared. And then, yes, you have to plug all that into your calculator, and when you do that, you get 1.460393, and there's your answer. All right, so that's using the midpoint rule. All right, now what do we have to do? Now they want us to give an upper bound for the error involved in this approximation. So the upper bound, that's going to be just like we worked this problem right here. And so what do we need? We need the second derivative, right? And then we're going to plug it into this formula right here. All right. All right. So let's go ahead and get started. So for part B, all right, we've got f of x is equal to e to the x squared. What do we need? We need the second derivative, don't we? So I've got f prime of x is equal to, what is that? E to the x squared times 2x, right? E to a power, the derivative is just e to that power times the derivative of the exponent. And then f double prime of x, well, that's product rule. That's 2 times e to the x, 2 times e to the x squared plus e to the x squared times 2x times the derivative of the exponent times 2x. And so I get f double prime of x. I'm going to factor out an e to the x squared. So that's going to leave me with, that's going to leave me with 2 plus 4x squared times e to the x squared. All right. So let's see what we have here. All right. So let's talk about getting k, because that's the more complicated part of it. So let's jot down what we know. We know that x is between 0 and 1. Okay, we know that because there's our limits on our integral. It's between 0 and 1. And so one thing that tells us is that x squared is going to be less than or equal to 1. We all agree with that because, we're plugging in a decimal or 1 Okay, so x squared is going to be it's going to be less than or equal to 1. So we've got f double prime of x. Okay, so f double prime of x is equal to 2 plus 4x squared times e to the x squared. All right, we know that. That's what f double prime is. And I know absolute value. We don't really need to worry about absolute value in this problem. This thing here is always positive. And we also know that this is greater than or equal to 0. All right. So what is this less than or equal to? Okay. What is this less than or equal to? Because remember up there in the formula, remember what it says. It says the absolute value of f double prime of x is less than or equal to k. That's what we're doing right now. That's what we're trying to find, k. All right. So we know that x is less than or x squared is less than or equal to 1. Okay, so this value here is never going to be larger than e. Okay, now keep in mind here, I'm just looking at this part. I'm not looking at this part over here. Okay, I'm not looking at that part just yet. But understand that this term here, this e to the x squared, is never going to be larger than e. Okay, so I'm going to put e right here because it's never going to be larger than that. That's the largest that term will be. And now what about this term? What's the largest that it can be? Now, and keep in mind, we're only looking at values between 0 and 1. All right, so what's the largest this value can be? Well, if I plug a 0 in, that's 2. If I plug a 1 in, that's 6, right? So I plugged in 0, I plugged in 1, I got 2, and I got 6. Well, what happens if I plug in 0.5? Is that going to give me a value larger than 6? No. So the largest this is going to ever be is 6. And look at that. There you have it. K is equal to 6e. And like I mentioned before, yes, you can choose a larger value for k, but remember, to get the more accurate results, we want to pick the smallest, largest number. Okay, the largest number that's the smallest. I mean, we don't want to pick 1 million. Okay, all right. And so now all we do is we plug everything in. So we get, let's see what we get. We get this is equal to k, which is 6e times b minus a cubed over 24, right? Over 24 times n squared. And so what would that be when we plug that in? We get 0.007. So there's the upper bound for our error. All right. So, I mean, it's not that bad. And like I said, don't forget, I've got more examples of this type of stuff. The errors in some other videos, they're just single problems. Each video has one problem. Like I said, I'll put the link to the description, put the links to those videos in the description. All right. So last thing here, we have Simpson's rule. All right. So Simpson's rule is if we have an integral f of x dx from a to b, that's going to be delta x over 3 times f of x naught plus 4f of x1 plus 2f of x2 plus 4f of x3 all the way to f of x sub n. Now notice what Simpson's rule does. The first and the last term, we're not multiplying by anything. But after we get past the first term, that's a 4 times 2 times 4 times 2 times 4 times. It's alternating 4, 2, 4, 2, 4. All right? Where n, okay, here you go, where n is even. So n has to be an even number. And then, of course, delta x, that's b minus a over n. Okay? All right, so here it says use Simpson's rule with n equals 10 to approximate. So we're going to approximate this again using Simpson's rule. All right. All right, so let's see. We've got delta x is b minus a over n. So that's going to be 2 minus 1 over 10, which is 0.1. All right. And we have n equals 10. So you just plug it in. So we've got 1 to 2, 1 over x dx, and that's going to be S10. I'll use the S for Simpson's rule, 10. That's how many, that's what n is. And so that's going to equal delta x. So look, I'm just plugging it into this formula. Delta x over 3. So that's going to be 0.1 over 3 times, and that's going to be f of 1, right? That's a. That's what we're starting with. And then we're just adding 0.1 each time. And so that's going to be plus 4 times f of 1.1 plus 2 times f of 1.2 plus 4 times f of 1.3. All right, so I saved you from the pain of having to watch me write all that down. So we've got everything written down. Make sure you're alternating the 4s and the 2s. And so this is going to be 0.1 over 3 times, and then we just plug each one in. That's going to be what? 1 over 1, right? Plus 4 over 1.1 plus 2 over 1.2 plus 4 over 1.3 plus 2 over 1.4 plus 4 over 1.5 plus 2 over 1.6 plus 4 over 1.7 plus 2 over 1.8 plus 4 over 1.9 plus 1 over 2. All right. And then you punch all that into your calculator, and we get 0.693150. And there's your answer. All right. And one thing that you can notice in this one, remember the actual answer is 0.693147. The trapezoidal rule actually gives us a better approximation than the midpoint rule. I don't know if, did I say trapezoidal rule? If I did, Simpson's rule gives us a better approximation than the midpoint rule and the trapezoidal rule, because this is your actual answer, and this is what we approximated with Simpson's rule. All right, so now let's look for the error bound for Simpson's rule. So suppose that the fourth derivative of x is less than or equal to k for x between a and b. If the error of Simpson's rule is the error involved using Simpson's rule, then that is less than or equal to k times b minus a to the 5th over 180 times n to the 4th. Now, it's the same thing. It's just a different formula. That's all. Okay? It's just a different formula. All right, so let's look at an example. How large should we take in order to guarantee that the Simpson's rule approximation for 1 over x dx from 1 to 2 is accurate to within 0.0001? All right, so I've got f of x is equal to 1 over x, and this time I need the fourth derivative. So that's negative 1 over x squared. F double prime of x is equal to, what is that? That's going to be 2 over x squared. And then f triple prime of x is equal to, that's going to be x to the negative 2, so that's negative 4. No, I'm sorry. I think that should be cubed. And that's going to be negative 4 over x to the fourth. And then, did I do that right? No. That should be negative 6. I'm trying to do all this in my head. And that's going to be, what is that going to be? That's going to be 24 over x to the fifth. All right, 24 over x to the fifth. So we need to figure out what k is. All right, so how do we go about doing that? Well, I've got the fourth derivative of x. Okay, that's equal to the absolute value of 24 over x to the fifth. Now, once again, remember, we're between 0 and 1, right? We're between 0 and 1. All right. Now, oh, I'm sorry, not between 0 and 1. We're between 1 and 2. Say 1 and 2 right here. So what's going to give me, what's going to be my largest value? Well, if I plug the 1 in, right, that's going to be 24 over 1. If I plug in any number larger than 1 up to 2, this is going to give me a smaller value, right? Because that denominator is getting larger, the larger the number I plug in. So we know this is going to be less than or equal to 24. It's the same thing that we did when we were finding k earlier. Okay? Just remember when we found k earlier, we were using the second derivative, and now we're just using this one. Okay? All right, so now let's plug everything in. Well, let's write our formula down. So we've got this is less than or equal to, that's going to be k times b minus a, and that's to the fifth, over 180 n to the fourth. All right, so what do we want? We want this, which is 24 times b minus a, 2 minus 1 is 1, 1 to the fifth, over 180 n to the fourth. We want that to be less than 0.0001, right? We want it is accurate to within this. Okay, so that's what we've got to find. And so, well, solve. Let's say we got 24. Well, 24 times 1 is 24, and then that's going to be 180. This is going to come down, 0.001, and less than n to the fourth. And so I'm going to get n is greater than the fourth root. See, n greater than, I'm going to take the fourth root of both sides, 24 over 180 times 0.0001. So n is greater than 6.04. Okay, and so we get n is equal to what? 8. Don't say 7. Okay, don't say 7. It's 6.04, so that means n has to equal 8. And why is that? Because remember, where is it? No, not right there. Here it is. Remember this. n is even. Okay, so you can see to approximate using Simpson's rule, we only need n equals 8. Remember what we found in the other ones? I think it was, what was it? But it may have been a different problem. I don't remember. But anyway, remember we calculated 29 and 41 for n. Okay. All right. So we've got one more problem left. Use Simpson's rule with n equals 10 to approximate the integral e to the x squared dx from 0 to 1. All right. So for part A, I've got delta x is b minus a over n. So b minus a over n, that is 0.1. Okay, so delta x is 0.1, and we know n is 10. All right, so let's see what we've got here. So we've got 0 to 1, e to the x squared dx is equal to 0.1 over 3, right? I put a, let me see something when I worked. Yeah, I couldn't remember. I got to thinking on that previous problem, did I put the 3 in the denominator? And I did. All right. So 0.1 over 3, and that's going to be what? F of 0, okay? See, we're starting at A, and we're going to B, and that's going to be plus 4 times F of what? 0.1 plus 2 times F of 0.2, and yes, I'm going to save you the pain again. Okay, so I saved you the pain of watching me write all that down again. So you can pause it and copy it down if you want, but there it is. Okay, and what do we get as an answer when we punch all that into our calculator? We get 1.462681. So there's your answer. All right, so now to find the part B, estimate the error involved in the approximation. Okay, so this is part B. So I need to go and find the what? The fourth derivative. So the fourth derivative is equal to, and I already have this answer, so I'm not going to go through and work all of it. Yeah, it's going to be messy. You're going to have to use product rule. Look, we found the second derivative earlier. Okay, it's just like that. You just got to find the third, fourth, and fourth derivative. And you're going to have to use the product rule. But so you can check your work, the fourth derivative is this. All right. Now, it just goes back to the same thing that we talked about earlier. We know x is between 0 and 1, okay? Because that's our problem. It's between 0 and 1. And so, let me write this over here. All right. So we know that this error right here is, let me put less than or equal to. It's going to be less than or equal to what? Well, remember I told you this right here is never going to be more than e. It's never going to be larger than e. This one right here, well, I can plug the 0 in and get 12, plug the 1 in. What is that going to give me when I plug 1 in? Okay, so when I plug 1 in, that's going to give me 76. That's going to be the largest value that I'm going to get out of this. All right, if I plugged in 0.5, I would get something less than 76. All right, so this I know is going to be less than or equal to 76 over E. All right, so my error is equal to, and let's write the formula down. That's K times B minus A to the 5th over 180 times 10 to the 4th. And so that's going to be 76E. And then I've got, remember, A is equal to 0, B is equal to 1. So 1 minus 0 is 1. 1 to the 5th is 1 over 180 times 10 squared. I don't know why I put a 10 there. That's an N. 10 N is 10, so 10 to the 4th. And that is going to give me what as an answer? That's going to give me 0.000115. And there's my answer right there. All right. And that is the end of this video. So I hope this helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I will see you in the next one. And don't forget, I don't know if anybody's still watching now, but don't forget the examples in the description. Later.